When we've got a physical system involving forces, accelerations, velocities, putting Newton's second law into maths basically equates to solving a differential equation. If we keep our model simple, we often end up with a simple differential equation which we can solve. If we have a complicated model, including lots of forces, we're likely to end up with a complicated differential equation that's too difficult to solve. For a simple pendulum performing simple harmonic motion, we can write down and then solve a second-order linear differential equation. First, we draw the pendulum mass and the forces acting on it, its weight, mg, and the tension in the string, T. We add important parameters, the length of the string, L, and the angle from the vertical, theta. The angular velocity, theta dot, the angular acceleration, theta double dot. We resolve perpendicular to the string. Newton's second law for linear motion is F equals ma. The equivalent for rotational or angular motion is torque equals I theta double dot, where the torque is also known as the moment, and I is the moment of inertia. So, resolving perpendicular to the string, we get mg sine theta times by the distance L, and that's equal to the moment of inertia. So for a point mass, that's just m times L squared, and then theta double dot. And our theta double dot's in the opposite direction to the force, so we need a minus sign here. Our m's cancel, one of the l's goes, and we're left with the differential equation theta double dot plus g over L sine theta is equal to 0. And for a simple pendulum, we assume that the angle gone through is small, so theta is small. And that implies that sine theta is approximately equal to theta. So we make that substitution here. So theta double dot plus g over L theta is equal to 0. And we have our differential equation, our second order linear differential equation for simple harmonic motion. So how do we solve it? Well, as always with integrating or solving differential equations, we guess or recognise a solution. And we're looking for a function that when you differentiate it twice is proportional to itself, so that when we add its second derivative to it, we get 0. And the way we do it for second order linear differential equations is we write down an auxiliary function, which is a quadratic equation in m. So we write down m squared plus g over L equals 0. And when we solve this, it gives us a solution or a functional form for theta. So m is equal to plus or minus I times the square root of g over L, where I is the square root of minus 1. And that tells us that theta is of the form e to the plus or minus I root g over L times t, which seems a strange solution until we remember, or we're told, that e to the ix is equal to cos x plus I sine x. And so what we do is we take the real parts of this function, and that gives us a solution for theta of a cos root g over L times t plus b sine root g over L times t. And the exact values of a and b will depend on the initial conditions.